I wanted to start talking about one of the biggest ideas in all of linear algebra, vector spaces and subspaces. I encourage you to read section 4.1, and you will read that a vector space is a set of objects that behave and follow these 10 axioms that I'm not going to get into right now. I want to give you guys more of an intuitive feel about what a vector space is. So again, there is a more formal definition that I want you to know about, but you already know what vector spaces are. Some of our easy examples are all of R2. That's a vector space. All of R3. That's a vector space. In fact, R of anything is a vector space. So that's something you can just count on. You know a vector space. But when we talk about vector spaces, we've said from the early days, a vector is just anything that can be represented with a list of numbers. So this may surprise you. The set of all matrices, 2 by 2, is a vector space. So again, if I have a generic 2 by 2 matrix, A, B, C, D, where A, B, C, and D can be any real numbers, the entire collection of those is a vector space. Here's another fun one. This capital P with the little 2 below it represents all polynomial functions of degree 2 or less. That is a vector space. So, just wanted you to know that this is the world we're going to mostly be in, our classic R world, but just to open up what we mean by a vector, it can be anything that obeys those 10 axioms. So, we'll leave it there. The more important thing is, what is a subspace? And a subspace, first of all, is a subset of vectors inside a vector space. So, we already start with the vector space, and the more interesting question we're going to be answering is, do we have something called a subspace? Now, a subspace, I am going to give you 3 characteristics that they all must have. So here are the 3 conditions we're going to be checking to see if a set of vectors qualifies as a subspace. Number 1, it must contain the 0 vector. So for instance, if I'm in R2, it must contain 0, 0. If I'm in matrix 2 by 2s, that's the 0 vector. So, just what you think. The second condition is the set of vectors must be closed under addition. And the idea of closure is big in linear algebra, and all that means is if you take a vector and add it to another vector, their sum is also inside that set of vectors. So as long as A plus C, B plus D is inside there, it works. And the third condition, it must be closed under scalar multiplication. Take any vector, scale it with any real number, and you end up with a new vector. And as long as that new vector is also contained in this subset of vectors, it now qualifies as a subspace. So those are the 3 biggies. So let's look at 3 examples to help bring this together. First, let's consider the set of vectors in R2 with this condition, that x is always greater than or equal to 0, y is always greater than or equal to 0. So if you think about that for 2 seconds, you realize that's a fancy way of describing all vectors in the first quadrant. So let's check the 3 conditions. So a little visual here. So x greater than or equal to 0, y greater than or equal to 0, we are talking about Q1. Okay, so my 3 conditions. Does it contain the 0 vector? For sure. X can equal 0, y can equal 0, therefore it contains it. Let's check for closure under addition. If you take any vector in Q1 and add it to any other vector in Q1, are you still in Q1? And it turns out you are. And if you think about why, if you take any x value that's greater than or equal to 0 and add it to any other x value that's also greater than or equal to 0, you will have an x value that is greater than or equal to 0. Same with y. So I'm not going to go through a formal write-up of that. I just think that's intuitive enough that we could agree that if you start with any 2 vectors in Q1, add them together, you're still in Q1. Check. So finally, let's check for closure under scalar multiplication. And here's where it falls apart. If I take, all I have to do is show one counterexample. So the easiest way is to think of a vector in Q1, let's say 3, 2, and let's scale it by any real number. Remember, that's what the scalar is. It can be anything on the real number line, as simple as -1. And of course, that takes me to -3, -2, which is no longer in Q1, but is in Q3. So no, did not remain closed under scalar multiplication. Therefore, this set of vectors, which is in a vector space, is not a subspace of R2. Again, R2 is a vector space, but the collection of vectors in Q1 does not warrant being called a subspace of R2. Okay, let's look at a second example. Let's call this collection of vectors in R2 the set of all xy vectors such that x times y is greater than or equal to 0. So if you think about that, if I take any 2 real numbers and multiply them together, they have to be greater than or equal to 0. Essentially positive, but could be 0. So think of all the set of vectors that do that. Well, if x and y are both positive, that works. Or x and y are both negative, that works. So it looks like, again, a fancy way of saying all vectors in Q1 or Q3. So I like to picture that. So like we had before, we've got this happening. So 3 conditions. 0 vector, bingo, not a problem. So let's try that one condition that foiled us the last time. Closure under scalar multiplication. So let's think about it. If we take any vector in, let's say Q1, we know they're both positive. So again, if I'll just use an example, 3, 2. Well, what got us last time was if we scaled it by a negative number, we ended up kicking it out of Q1. But notice where this lands is in Q3. I think we're okay. So, and the reverse is going to happen. If I take a vector that's already in Q3, scale it by a negative number, it kicks it into Q1. And of course, if I scale by a positive, we stay in that quadrant. If we scale by 0, I get the 0 vector. So I think this condition is okay this time. I love it. So let's try that last one. Let's see if we are closed under addition. And this is where it falls apart. With a counter example, there's a vector in Q1. Let's add it to a vector in Q3. And we end up with this example, -1, +1, whoops, a vector in Q2. Not closed. Frowny face. So again, what did we start with? A subset of vectors in R2. But because we lost out on that third condition, it is not a subspace. Of R2. All right, third example. Let's talk about the collection of vectors where x is always twice y. So let's picture a few of those. For instance, that could be 2, 1. It could be 6, 3. It could be -8, -4. So as long as the x is twice y, that qualifies to be part of this collection. Okay, so I have a set of vectors in R2. Do they qualify as a subspace? Let's go. Step 1. Does this contain the 0 vector? In other words, is 0 twice 0? And of course, it is. Check. We're good. Let's try closure under addition. If you take any two vectors where x is twice y and add them together, does that hold? Well, let's check with a generic look. How about I take a vector, 2a, add it to another vector where the first entry is twice the second entry. What do we end up with? Well, if I add 2a plus 2b, I get 2a plus 2b. If I pull that 2 out, I can see that that's twice as much as just a plus b. Yeah, it always holds. So closed under addition. And finally, what about closure under scalar multiplication? Well, let's again start with a generic vector where the top is twice the bottom. Let's scale it by any real number. And what do we end up with is 2 ACs and AC. Yep, it holds. So, for our third example, we finally see a subspace. So, yes, subspace. In fact, what is the visual of what's going on here? Let's move my camera a bit. And what are we talking about? Is the collection of vectors where x is always twice y. I think we've got ourselves a line through the origin in R2.